Hi everyone! Today I'll be explaining IPv6 DNS. So, what is DNS? It's short for Domain Name System, which is a distributed database used for translating domain names into IP addresses. It supports both static and dynamic resolutions of domain names. For static resolution, we need to manually create a domain name resolution table. Add the desired domain names to the table, and map them to IP addresses. As you can imagine, the workload involved in static resolution increases as the number of mappings increases. That's where dynamic resolution comes in. Dynamic resolution enables user programs to access a DNS server through a domain name resolver on a DNS client. Packets are typically forwarded across network boundaries using the Internet Protocol, or IP. To guide packet forwarding hop by hop, IP uses IP addresses as destination addresses. This means we can use IP addresses to visit websites. However, we rarely do so, and instead use domain names. Why is this? Although we can use IP addresses to visit websites, remembering a string of irregular numbers is difficult. That's why we use domain names, as they are easier to remember and often more descriptive. Say we want to visit Huawei's official website. We can enter Huawei.com, which is far easier to remember than an IP address. DNS will then find the corresponding IP address so that we can visit the website. Each computer is configured with a local DNS server. When a website address needs to be translated into an IP address, the local DNS server queries the pre-configured authoritative DNS server to obtain the IP address. Sometimes, multiple queries are involved in obtaining the desired IP address. The pre-configured authoritative DNS server is responsible for responding to the local DNS server. If the local server queries the IP address of a domain name, but the authoritative server does not know the IP address, the authoritative server returns information about another authoritative server that may know the IP address. The local DNS server then queries this new server. If the new server doesn't know either, this process repeats until the local DNS server obtains the IP address. If the local DNS server knows where the authoritative DNS server is, it directly queries this server. Otherwise, the local server first queries a root DNS server. The root DNS server then tells the local DNS server which authoritative DNS server it should query. DNS servers typically cache the mapped IP addresses and domain names to speed up future queries. But what is the resolution process if there is no cache? Let's first look at the levels of domain names. .com is a top-level domain name. Huawei.com is a level 2 domain name. And www.huawei.com is a level 3 domain name. After a user enters a website address, the local DNS server first queries the root DNS server for the top-level domain name. Let's use Huawei's official website again as an example. After receiving a query from the local DNS server for the IP address of Huawei's official website, the root DNS server returns the name and IP address of the authoritative DNS server for the top-level domain, namely .com. The local DNS server then queries this authoritative DNS server, which returns the name and IP address of the authoritative DNS server for the level 2 domain, namely Huawei.com. The local DNS server then queries this authoritative DNS server. Because this DNS server is the right server, it provides the IP address of Huawei's website to the local DNS server, allowing the user to visit Huawei.com. In this process, the root DNS server plays a vital role, as without it, there would be no subsequent queries. Each country has its own country code top-level domain name. Theoretically, if this domain name is masked on the root server, the corresponding website will disappear from networks. This means that someone in control of the root servers could compromise a country's network borders and network sovereignty. For example, by preventing a country code top-level domain name from being resolved, a malicious actor could block access to all websites suffixed with the top-level domain name. This is indeed worrisome. Luckily, we have root mirror servers. A root mirror server has the same functions as a root server. The most important thing on a root DNS server is the root zone file, which records all top-level domain names. A root mirror server synchronizes data from a root server, meaning that they eventually have the same root zone file. Generally, requests to a root server can be completed through a root mirror server. But what would happen if the root DNS server's root zone file was maliciously altered? Would the root mirror server synchronize this modification? We do not need to synchronize the modification, as we maintain the root mirror server and can control what it contains. Therefore, the impact on us is controllable. After explaining the basics of IPv4 DNS, we can say that it has certain limitations. So what about IPv6 DNS? Active development of IPv6 drives more mature technologies, facilitating strong network autonomy and risk avoidance. Therefore, it's imperative to apply IPv6 DNS. Now, let's have a look at the current situation of IPv6 DNS. IPv6 DNS and IPv4 DNS have the same hierarchy. DNS, a vital component in the Internet, supports the transition from IPv4 to IPv6. It also supports IPv6 address hierarchy and address aggregation. IPv6 DNS has been deeply researched in China. It's much easier for IPv6 DNS to support functions such as automatically identifying dangerous domain names, restricting the number of concurrent recursive queries, and limiting the DNS resolution rate. IPv6 DNS also allows you to configure flexible resolution policies and different resolution modes to schedule traffic. To summarize, we've seen how important IPv6 DNS is and how the DNS resolution process works. While there is room to improve IPv6 DNS, hopefully it will become widely adopted as IPv6 gains popularity. Thank you for watching. See you next time.